Hey yo, what's up guys? Baby Bear 4812 coming at you one more time. Welcome to part one of a three-part series on constructing binary trees from various traversals. So LeetCode's got three different problems. We've got the one we're looking at today, which is construct a binary tree from a pre and in order traversal. The second one is post order and in order. And the third one after that is post order and pre-order. The reason I wanted to put this series together is because I think that there's a way which is logically consistent across all three of those problems where if we can really learn how to solve one, we can build up and solve the others just as smoothly. Although I would argue that they are kind of an increasing level of difficulty in my opinion. So like I said, we'll be going through them one by one. This is the first video. We'll walk through the logic on how to think about this problem, how we'll build it out, and then I'll kind of build out a clean code template that we'll then be able to reuse for the following two problems. So without further ado, if you haven't tried this already, of course, pause the video, give it a shot. But let's dive into it. We're pretty simply, we're given a pre-order and in-order traversal of a tree, and we need to construct that binary tree. We may assume duplicates don't exist in the tree, and they give us this example here where, well, you see right here, 3, 9, 20, 15, and 7 is our pre-order, and the in-order is 9, 3, 15, 27, and the resultant tree is this. So relatively, I'd argue, straightforward problem in terms of just understanding what they're asking for. We'll walk through this example in a bit more depth now and think about maybe how we'll go about doing this. So what I've done is I've pasted out, or copied over, I should say, the exact pre and in order traversals, and two things that I want to bring up. The first is let's actually remember what the definition of these traversals is and how we do them. With the pre-order traversal, we first look at the node itself, which I've kind of called a root here, and then we check the left child, and then we check the right child. With in order, we first check the left child, then we check the root, and then we check the right one. And this is all done recursively, okay? So this isn't going to be an introductory video on how to do these traversals. I'm assuming that you have some, working understanding of how to do these. So, we think about then what the tree will end up looking like, and fine, I think we'll kind of build it out. I don't want to draw it out just yet. We'll build it out as we go here. But the logic behind it is this. The first thing we need to notice is that each one of these contains both the root of our tree as well as some left subtree and some right subtree. And of course, that'll recursively break down further, but we need to begin by acknowledging this. The question becomes, out of this traversal and this representation, which part of it is the root, which part is the left subtree, and which part is the right subtree? Well, for that, we turn back to the orders here, the order definition. Pre-order is usually a very convenient one for the following reason. And it's because since the root always starts first, we know that the root of the tree must be right here. Maybe I'll give myself a bit more space. We know that this must be the root, okay? The root is then preceded by all the left children and then all the right children. So there's some breakdown of any given pre-order, so maybe I'll even just generalize this. With any pre-order traversal, you've got your root. You've then got your left subtree. I'll call that LST. And then you've got your right subtree, okay? The tricky part in these questions is actually determining which part is which. So how big is this left subtree? I mean, is this the left subtree? Are these two the left subtree? Are all of these the left subtree? Maybe the entire, everything after the root is part of the left subtree. And with the way that these traversals are represented, we don't know without having at least another traversal. If you've watched my previous video on serializing and deserializing trees, the way that we serialize those was a bit different, and in that case we could use only the pre-order to actually build out the tree. And the reason we could do that is because we actually acknowledged where all of the null nodes were for the children. So if you kind of walked in order, you could build it out very simply. But we don't get that here. And so we somehow need to use these two in combination in order to decide what the breakdown of this tree is. Similarly, for a generalized in-order traversal, we can acknowledge that since we go left and then the root and then the right, we'd have something like this. We have a left subtree, then we identify where our root is. I'm sorry, I think you guys hear the background noise right now. It's just my computer heating up. I'm sorry about that if the audio is a bit annoying right now. And then we've got the right subtree right here. Okay, so this is the general breakdown. How do we pin these together and acknowledge these and then build this tree out at the end? Well, think about it this way. We know that this is our root here. Okay, this is our root. In the INORDER, we can find this root. We can walk through it, or we can use a hash table, which is what we're going to use to kind of store where all these values are. Well, this right here is my root, right? It's the same value 3, so these represent the same node, or the same value of the node. All right, that's cool. So how does this help me? I still don't know what the left subtree and what the right subtree are here. But with the help of the INORDER, we can notice that the root falls between the left and the right subtrees. What this means is that everything to the left of this root must be in the left subtree. Everything to the right of it must be in the right subtree. And what we can do with this information, when we kind of acknowledge where the root falls within the INORDER traversal, we can immediately tell, just to the left of this root's index, we've got the entire left subtree. So maybe from one step over all the way to the beginning of the array. And then from one step over all the way to the right of the array is the right subtree. And that makes this really convenient. In fact, the first two problems in this series are pre-order INORDER and post-order INORDER. The INORDER is really convenient, and it'll make this question a lot easier. When we have just the pre and post order, those will be a bit trickier, and we'll deal with that in the third part. So I hope overall that this logic makes sense. And the way we're going to build this thing out is going to be kind of as follows. Maybe, I don't want to delete that. Maybe I think I want to scrap this. So I think you guys get this here. This was important. I'm going to delete that. I'm going to go back to my pen here. And let's at least logically think through how we now put this together before we do the code. If I notice that this pre-order right here, that first item is my root, easy. We've got the root of our tree, and that's 3. Now I need to make a recursive call on whatever function I'm making that's going to build this tree out for me. So I need to say root.left equals some set of traversals, and root.right equals another set of traversals. Well, if I call root.left, I'm going to want to call it on everything to the left right here. So to the left of this root 3. In that case, this is going to be a 9. And so I'm drawing it like an array here. I won't be passing through an array. We will just be able to pass in indices. And given terminal conditions, we'll be able to pick out, we can say if we just have a length of 1, or if our start and end index are equal to each other, we're just going to create this node and return it. Otherwise, here then on the right side, we're going to need to pass in everything to the right of the root, which will be 15, 20, and 7. Okay, that's kind of our step 1. From there, every single time we're kind of moving on, what we're going to do is we're going to keep one pointer on the pre-order traversal, and we're going to walk through with the pre-order one item at a time. Every time I walk through with this one item, I'm going to check where that item falls in the INORDER. Okay, I'm going to create this node. I'm going to say this is my new root, again, for every item as I go here. And then I'm going to recursively say, find it. So if I'm looking at the 15, I'll say find this root. Everything to the right, is a left subtree. Everything to the right is the right subtree. Everything to the left is the left subtree. And again, obviously, it depends on what we've got going on here. So we're going to be playing around with the 2 pointers. That we're going to be passing through this function in order to actually determine when we've kind of reached the end of the tree. I hope that explanation, especially toward the end, wasn't too vague. I do think this will be a bit more clear when we dive into the code. But more than anything, if you can kind of follow along with this part that we got going on right here, the first thing that we determine, then from there we can actually base our code, the recursive call, on this logic, and the rest will take care of itself as it normally does. Now, what I'll do is so I already have kind of the pre-written a bunch of the code as I usually do, but I'm going to follow it verbatim this time. So I'm looking at it here on my phone, and the reason I'm going to be strict about it is just because, again, I want to build this out as like a really clean template, so that when you compare this question this video to the rest of them, you can see the exact kind of code, almost replica, line for line. It'll make it a lot easier to follow along. So the first thing we want to do, as usual, is to do some error checking. And this error checking I'm going to do as follows. We were just going to say if not pre-order or not in order. So if either of these is empty, I'm just going to return none. I don't think we weren't really given any constraints here in this problem, so there isn't much to go off of, but we'll just assume that'll be kind of enough basic error checking. I'm then going to have some sort of builder function, and I don't know what I'm going to put in there yet, but we're going to have some sort of recursive call that we're going to need to be calling in order to build this tree. Eventually, I'm just going to want to return return this builder function. I don't know, again, what I'm going to do with it yet. But before we dive into it, there are two things that I'm going to need to do that refer to what we kind of talked about here. One was the fact that we said that as we're traversing through this, we're going to keep an index on the pre-order, and we're just going to move it along one item at a time. So what I'll do is I'll declare a variable called pre-index and set it to 0. It'll start at the beginning of the array. And then the other thing which we said, which it's not strictly necessary, we can solve the problem without it, but it'll largely help the time complexity, which will be here, by the way, will be linear time and linear space. What we're going to want to do is almost build a map. And then for this map, what we're going to want to say is, if I look at the value 3 here, I want to know where that value 3 falls within the context of the in-order traversal. Reason being is now I have that index and I can kind of make my calls to the left and right subtree a lot easier, and I don't have to walk through the entire in-order array every single time in order to find the item that I want. So what I'm going to do is I'm going to call it in for in-order, so in index map, and we'll just make it a dictionary. And super simply, we're just going to enumerate through the in-order. Through the in-order traversal. So I'm going to look at the index and the value at every step of the way. And I'll say that's in enumerate in order. So again, enumerate gives us both the index and the value at that index at every step along the way as we walk through an array. And I'm just going to say index, in index map at my value is equal to index. So what this will tell me again is if I come across this 3 in my pre-order traversal, and I'll want to say where is this in my in order, and it will return that it's at index 1, right? So once we've actually done this, we can this is a bit of pre-work here, no pun intended. We can dive into building this recursive call now. So as I mentioned, we're going to be interested in knowing where our left and right subtrees fall at any given time, and we don't necessarily have to pass in an array for that. What we'll do is we'll pass in 2 pointers, like a start and an end pointer for the subtree that we're dealing with, and we're going to adjust them accordingly if we're building a left or right subtree. So again, if that doesn't make sense just yet, bear with me and I promise we'll get there. I'm going to call them in start and in end, as in the pointers in the in order traversal, and they're going to be start and end, like a left and right, if you will. And by default, we're going to start the leftmost part of the array, which is 0, and we're going to end it at the rightmost, which is at the end. This will also take care of the fact if we've got an input of like just one item in either of these traversals, it'll be a very clean solution. Now we have a few conditions here that we're going to deal with, and these are going to be our terminal conditions. So what happens if our start index, so if in start is greater than in end, we're going to have to deal with something. Again, we don't know what this something is, and we will in a moment, but let's kind of build the logic out. We then need to say what's going to happen if they're equal to each other. So right now, that would be the case if I'm trying to build a subtree, but both of them are pointing at the exact same item. So what does that actually tell us? And finally, if they're not, that means we're passing in some range of values. We're actually going to have to get into more recursive calls. So let's think about it this way. If we get in some sort of gibberish answer where the start is after the end, so left is greater than right, that's really not going to help us with anything. And at that point, we've kind of gone too far, and maybe we've already built that part of the tree. So if this happens, we're just going to return none. That means we've hit a null node. And again, if this isn't clear yet, I think after we build out this logic, then this will make a bit more sense. Then okay, if they're equal to each other, then what we're going to want to do is we're actually going to want to just return that node. So they're both pointing at one node. And think about the scenario again where you're passed in a tree or in order traversal and pre-order traversal, it's just one element. The start and the end are going to be at the same point. And what we'll do is we'll create some sort of node called, it's going to be part of the tree node class. And we are going to do what with it? Well, we're going to have to take the pre-order, and out of the pre-order, the value that we're pointing at, we're going to need to do something about, well, not do something, we're going to have to actually create this node. And the way we're going to do that is, again, we're walking through this pre-order one item at a time, and I have a pre-index that I defined right here, and that tells me where I'm actually sitting and what value I want to make. So I'm going to take the pre-order array at the pre-index that we're currently at, and we're going to return this node. Now, what else? The other thing I'm going to have to do is I'm going to have to take my pre-index and move it along by 1 unit, if that's the case, because, well, same thing we're going to do here. With every recursive call I make, I'm going to want to advance that pointer by 1 so we can keep building the rest of the tree as we go. with that, I'm gonna have to declare it pre-index as a non-local variable because it exists just outside of this function scope. It's within a bigger function, but since we're actually modifying it, I'm gonna get an error if I don't declare non-local. Now, these are two kind of edge cases or terminal conditions, and now this else here is redundant, so I'm just going to get rid of it, but this is gonna be where the bulk of the function goes. So I know that I'm gonna have to, build out this this part of the tree, and I've jumped into my recursive call, and I'm now looking at my root. Imagine we're making this call for the first time, and I'm sitting pretty right here, and I know that this first item is going to be a root because again we go root and then left and then right. So what I can do is I can say I'm gonna determine what the value of this root is. I'm gonna see where the index of it is within the in-order traversal, and then finally I'm gonna set it equal to something to this node we're going to create. The reason I'm breaking it out into 3 different lines here, strictly speaking, you don't need to do it. I just think for legibility in the code, it'll be a lot easier to understand if I split them out item by item. Sorry. So the actual value of it will pretty much be exactly what we did up here. We determine the value by taking the pre-order array at the pre-order index that we've got. So that's going to be the value of it. And now we need to know where it falls within the context of the in-order array. Well, the index that it'll be at will be at our in-index map right over here. And the value that we're interested in is root value, the one that we just created. So again, you could have hypothetically made this call right here and had it kind of nested. Again, I just think this was a bit cleaner to deal with, which is why I've modularized it a bit. Then finally, we're also going to want to build an actual tree node, and we're going to do it with the value of root val, which we found up here. And so this has actually now created our root. Now that we've created the root, we've said, okay, I've done this thing. I'm going to move my pre-index up by 1 because if I now want to make my subtrees, I'm going to need to have that index moved further along. And so I'm going to need to say, what's my left subtree? And I'm going to have to say, what's my right subtree? And then after all that, I'm going to have to return the root. So imagine, again, making this call where we go through this in our first step. We get to this 3, we say, okay, I'm going to create this root node right here. I've created it. I'm going to move my index along, and then now that it's moved along, I can actually take care of recursively making my left and right subtrees. After I've made those and the recursive stack kind of pops back up, and we get to the end, I'm going to return this root, which is ultimately returned here as the entire binary tree. So for the left call, we need to see how exactly we're going to build it. And namely, what we need to determine is what these start and end indices are of what we're building. So let's think about this. These indices are in the actual in-order traversal, right? That's why I call them in start and in end. If I found my root right here, so this is root index, okay? Everything to the left of root index is part of my left subtree. So I need to start and end before that value, meaning that I need to start with in start, which whatever that default was, for example, if that was 0 right from the start, I'm gonna have to start there and include all the items up to, but not including the root itself. So up to but not including means taking the root index, which in this case would be this 3, but 1 less than that. So root index minus 1. For the right subtree, we're going to want to start, think about here, not from the root, but from 1 after the root and go all the way into the end, okay? And all the way until the end is, or rather, root index plus 1 is where we start, and then in end, whatever that value that we're passing down is, will be the actual, end of this traversal, and that'll be our entire right subtree. What I'm going to do here is I'm just going to run this really quickly and make sure there were no mistakes, which there were on line 31. Oops, I think I meant in order here. There we go. I'm going to submit that super quick. Perfect. That runs. And okay, so I wanted to make sure that I didn't make any dumb mistakes before I kind of summarized the video. So in this video, and I don't know why the runtime was so here. By the way, all of these were built on the same code, so it could be almost half that time if you're, yeah, don't worry about those. But anyway, so what we did was we did our basic error checking. We defined the fact that we acknowledged here what the actual traversals look like, what the order of them is. And from there, one of the key insights we gleaned was that drawing I had earlier of understanding that in a pre-order, we've got the root, we have some distance of a left subtree, and then some length of a right subtree. And for in order, we got the root somewhere, and then everything to the left is a left subtree, everything to the right is a right subtree. And once we acknowledge that fact, then we can actually piece together what the relationship is between these and how to work together with these two traversals in order to, by moving one item at a time through the pre-order, always defining where, what the rest of the subtrees look like on both the left and the right side based on the in order that we were given. To make it a bit quicker, we did create this mapping over here to help us check where the value of the pre-order item we're looking at falls in the in order. So that was just one small optimization. And then the rest, I hope, was relatively straightforward in terms of actually creating the root, moving the index up, and then just saying, well, this will create my left subtree, and this is going to create my right subtree. If you guys have any questions on this, and again, sorry, I have been getting feedback on the time and space complexities. I do forget them sometime. I know I mentioned it earlier, but this is linear time, linear space. I'll put that in the description below. But if you guys have any other questions on the solution, any feedback, drop it down below. I'm happy to address it. If you haven't already, subscribed, liked, commented, shared, all that fun stuff, please do. It does help a lot. And that's all. I guess I'll see you guys next time. Peace.